In this example, we're going to look at the response of a second-order system to a sinusoidal input. We have here a simple spring mass damper system. We just have the main mass m, 1,000 kilograms, attached to a spring, 10 to the 7th newtons per meter, a damper at 1,000 newton seconds per meter, and on top of this, we have this rotating mass. And that mass is going to be providing a vertical force up and down as that mass rotates around its central pivot. We are going to be ignoring the horizontal forces and only considering the vertical forces, keeping this a single degree of freedom, which is denoted by x here. And what we're going to be looking at is when we turn this on and when we rotate it at 100 radians per second, and that mass is spinning around, what is going to be happening to our system? And we're going to investigate that through a Bode diagram. So we're going to start by looking at our simple spring mass damper system. And here we have a free body diagram drawn for it. So we have our mass, which includes that machine and the little pedestal it's on as big M as the mass there. So the forces acting on it are going to be from the spring and from the damper. So if we say that x is positive down, we'll have a negative kx and negative bx dot acting on it. We have the force from the rotating mass, so that is going to have a force of mr omega squared sine omega t. I have a link to where that is coming from. And this is little m, it's the eccentric mass, the rotating mass that's used here, not big M, that's the mass of the whole pedestal. But we do see on the right-hand side in our inertia picture, we have big M x double dot for the inertia of this object. So if we do the equations of motion for this, and we simplify it up a little bit, we have our left-hand side has our x terms, and I am going to leave in terms of p of t. I know what p of t is, but that will come in a moment. The transfer function, I'm just going to be looking at my output over my input. So I'll leave it as, when I do my Laplace transform, as capital P. I'm not going to put in the known value yet. So if I take this equation, I do my Laplace transform, then I get x over p to be as we've been seeing before, the 1 over ms squared plus bs plus k. If I now put in the values for m, for b, for k, we see that we have the 1000x squared plus 1000s plus 10 to the 7th. And I do want to do some analysis with this, put it into that standard form we've been working with. So I'm going to divide everything through by 1,000. Again, I haven't changed the transfer function. I can put either of these two versions of it into MATLAB to make the Bode diagram, and it's going to look exactly the same. It is the same function, but we're going to be able to get some additional insight in that last form where we have the s squared term with a coefficient of 1, because now we're going to be able to look at this and we can look at what's the natural frequency going to be, etc. So if we take this form of it, and we're going to start there, it's in our standard form that we like, so we know that in the denominator, the constant term is going to be equal to our natural frequency squared. So if I take the square root of both sides, we find that this system has a natural frequency of 100 radians per second. And if we look at that middle term, the coefficient of 1, we know that that's going to be 2 zeta omega n when we're in standard form. So 2 zeta omega n must be equal to 1. So now we can solve for zeta, the last thing we don't know, now that we know the natural frequency. So we have a zeta value of 5 times 10 to the negative 3. It's very small but positive. It is between 0 and 1. This is a damped system, an underdamped system specifically, but we have a very little bit of damping. And we're going to see that that does influence what the Bode diagram is going to look like. So what we can do now is head into MATLAB. Right, now in MATLAB, I can make my transfer function. So I'm putting in my values m, b, and k that were given to us. And I'll calculate along the way the transfer function as well as the resonant frequency. We'll come back to that in a second here. So I'm making my transfer function g. I'm just using that original form, 1 over ms squared bs plus k. Again, we can use either form, or when we divide everything through by m, both are going to work. And I'm making the Bode diagram in this example manually, as we see in 59 here. So I am saving out from Bode this m and this phi. So it's a list of my magnitudes and a list of my phases that are coming out when I use Bode in this way. I could just use Bode of GW like before and have it automatically make the Bode diagram, that's okay. Here I just want a little bit more control over the Bode diagram that is coming out, and I'm going to do it by kind of taking this data and then manually making the Bode diagram. So that's what I'm doing in 61. It's going to look very similar to what MATLAB makes, but again, this is a little bit customized. So I'm making the subplot. This is going to be the magnitude. And interestingly, when we use Bode this way, where we get this vector m and this vector phi, let me run it up to this point. We get a vector of our m values that comes out as this three-dimensional matrix and phi. And I actually fixed that in 60 to make it something more usable. So now if I relook at m, it's just a list of values like we're used to, and the same is true with phi. It's just a vector of values. The m that comes out of here is actually not in decibels. It's actually the linear ratio, and phi will be in degrees. So even though it does automatically plot it in decibels, the m that comes out is linear. So I am actually going to stay in the spirit of the Bode diagram and plot it in decibels. And that's what I'm doing in this section here in my subplot. So I'm making my Bode diagram. I will make a semi-log plot in the x direction along the x-axis because the frequency is in log scale. And I am, you see in 63, converting into decibels, so 20 times the log 10 of the m that came out of Bode. So let's start there. And if we get our figure so far, this is going to be our magnitude in decibels. And then the second part of this is going to just plot my value of phi. And then I do some things down here to just add labels and everything else to it. So yeah, I'm just making the Bode diagram, but a little bit customized from what we see it automatically produce. So this is the Bode diagram that we get. So if we look at the magnitude, we clearly have this spike. It is a second order system. We have this spike and it's occurring at 100 radians per second, or very, very close to it. Now, if I go back a second, I am calculating this resonant frequency the way that we saw it before, but our zeta value is very, very small. So we see that the resonant frequency, we get 99.9975. It's barely different than the natural frequency of 100. So the low damping, the resonant frequency, the natural frequency, basically the same. And that's, again, where this spike is occurring. So it's saying it's 100. Technically, it should be a little bit to the left, but it's more or less at 100 radians per second. And we see in our phase diagram, we have that inflection point also at 100 radians per second. So again, the transfer function is what's creating the Bode diagram. The transfer function doesn't know up front what the input is. When we go back to the prompt, now we see, okay, we want to drive this thing, the value of omega, that input frequency is meant to be 100 radians per second. But we are presented with the problem that from the Bode diagram, our system has its natural frequency at 100 radians per second, and also, more importantly for this, the resonant frequency is about 100 radians per second too. So what that spike tells us is that magnitude is going to be relatively much higher of our output. The position is negative 100 decibels if we drive the system at 100 radians per second. Now, typically that's not going to be good. We don't want to operate near that peak because we're going to have a very high output amplitude when we're near that peak. Now, it's going to be typically a relative maximum because we see it is negative 100 decibels. But again, this is log scale. So getting away from that peak, we're going to get closer to, let's say, like negative 140 decibels. So much less amplitude in that output as we get away from that peak. And if we drive it faster, we see that it's actually going to reduce as we increase the input frequency. And if we reduce the input frequency, it's going to really level off. It looks to be around negative 140 decibels. So let's say the problem in this we're facing at the moment is we must drive this machine at 100 radians per second for one reason or another. Maybe it's in line with other machines that must rotate at the same frequency if it's on a common axle, say. But the whole machine, it resonates at that frequency. So we have a design problem that we don't want to operate near the resonant frequency, either change the input frequency. Let's say that's not an option. So what would another option be? Another option would be maybe we can change the the base that machine is sitting on. It's sitting on a spring and a damper. Now, this is not always possible. Let's just say we can add another spring to it, and effectively that's going to double that equivalent spring constant. It's going to go from 10 to the 7th to 2 times 10 to the 7th. How is that going to affect the response of the system? Well, let's again go back into MATLAB and take a look. Back into MATLAB, we see it's basically the same code. M and B are still 1,000, and K now is 2 times 10 to the 7th, so doubling that spring constant. So let's see what this does so far. Our natural frequency, if we calculate it longhand, or we calculate it here, we get 141 radians per second. Doubling the K increased our natural frequency by a factor of really √2. So we have a different natural frequency. Again, we have very low damping, so that resonant frequency more or less the same. So we've shifted the resonant frequency of this system by doubling the spring constant. And everything else is going to be identical. I want to make the Bode plot for this new modified system. So making the Bode plot, making it a little bit larger. That peak is going to occur at the resonant frequency. So again, about 141 rounding to 3 digits is where that peak is. However, the part of the problem remains the same of we want to drive this at 100 radians per second. Well, that's back over here. So we see that at the peak, we're at negative 105 decibels. However, where we actually want to drive this system at 100 radians per second, we're down to negative 140 decibels. And recall in the previous iteration of this, we were at negative 100 decibels. So we've dropped by 40 decibels, which is going to translate to a lower output amplitude. So in this example, we were able to shift the peak of the Bode diagram to the right by modifying the parameters of the system itself, namely by doubling what the spring constant was. Now we're going to see that's, again, not always possible. We might not be able to modify the machine, the K, the B, the M of the machine. However, we might be able to. Another thing we could have done in this problem is maybe if we increased the mass, we added more weights to it, that also would shift where this peak is, because we are going to be changing what the natural frequency is and thus also changing what the resonant frequency is. And finally, maybe changing the damper would have changed a little bit. We can shift this peak again more to the left if we increase our damping, because the resonant frequency is going to drop relative to the natural frequency. But something like that might not be quite as effective as changing the M or the K. But we do have some options in redesigning our system if we must drive near the original natural frequency or resonant frequency of our system.